Well, welcome back to this discussion about solving trig equations. And in this installment, we're going to focus our attention on trig equations that have more than one trig function within them, but they can be taken apart by factoring. Okay, so we're going to take something that has two trig functions and separate them into factors that only have one. So this technique is one of the easier techniques, so I think that you're going to find it simpler than some of the other things we've done so far. So let's jump in. We are looking in these examples to find the exact principal solution for each trigonometric equation. And remember, a principal solution is the same as finding all the solutions on one rotation of the unit circle. So from 0 to 2 pi, but not including the 2 pi. Okay, so in this strategy that we're going to focus on, we are going to notice that our equations have more than one trig function embedded in them, and we are going to try to separate those into separate factors. Okay, so that's the whole idea. First, you'll set that equation equal to 0. Then you will factor the resulting equation, and you're especially looking for a GCF here. Okay. Sometimes you'll have two binomial factors, but especially we're looking for a greatest common factor, and usually that will be a trig function. Then we'll set each factor equal to 0, and then isolate our trig function to solve for x. Now, since we are dealing with more than one trig function, it's possible that a solution generated by one trig function is going to become something problematic in the other trig function. So one thing that we need to watch for is to check your solutions in the alternate functions and reject anything that produces an undefined output. While this may not always be the case, when you have functions that have values that are undefined at specific places, those are the ones we want to especially watch for. So anytime you've got a tangent, a cotangent, a secant, or a cosecant, you're going to definitely check the values that come from the alternate function and check them within those functions to make sure you're not getting something that's undefined. And we'll see how that works in a little bit. For these first examples, they're already going to be factored for us. So we don't have to set them equal to 0 because they're all set equal to 0 and they're already factored. So we're just going to pick up here in this C and D for our technique, and there's a reason for that. As we look at how to do these problems, then we can go into the more advanced problems where we have to do steps A and B. Okay, so since they're already factored, we're going to set each of these factors equal to 0. So I have a factor tangent of x minus 1 times cosine of x plus 1 is equal to 0. So I'm just going to set each of those equal to 0 and then isolate the trig function. So move this negative 1 to the right-hand side here, move this positive 1 to the right-hand side here. So we would end up with the tangent of x is equal to 1, and the cosine of x is equal to negative 1. So now we can use our knowledge of the unit circle to answer these questions. Which angles on the unit circle have a tangent of 1? And that is where the y and the x values are exactly the same. So that would be at pi over 4 and 5 pi over 4. And where's the cosine of x equal to negative 1? What angle on the unit circle has an x value that's negative 1? And you should say pi there. So that's all there is to this technique for this particular problem. We just express our solution set as those three angle measures. Okay, now we see that one of these functions is a function that has values that are undefined. We know that tangent has areas on the unit circle that are undefined, right? And so we want to think about, if I plug in pi here, do I get a value out? Let's double check. If I take tangent of pi, is that defined? Well, yes it is. It's 0. Right? And that's, while that's not equal to 1, that's okay. We just want to make sure that we're not getting something undefined here. All right, so we have to double check those values. Let's just consider subbing in a value that would produce something undefined into this function. So let's consider that we got something undefined here, and something undefined minus 1 is still undefined. And then if we take that and then we multiply that by anything, it's still undefined. So we gotta check and make sure that we have defined outputs in both. So let's do these next couple of examples. Taking this equation, 2 cosine of x plus square root of 3 times 2 sine of x plus 1 equals 0. Let's take each of those factors and set them equal to 0. Now isolate the trig function. So in this case it's cosine of x, so we would subtract the square root of 3 and divide by 2. And in this case it's sine of x, so we would subtract a 1 and divide by 2. So we would end up here with cosine of x is equal to negative square root of 3 over 2, and sine of x is equal to negative 1/2. Now, thinking about our unit circle, which angles there have an x-coordinate of negative rad 3 over 2? Okay, and so that's going to be 5 pi over 6 and 7 pi over 6 for this equation. And now let's think about this one. Sine of x is equal to negative 1/2. Which angles have a y-coordinate of negative 1/2? And that will be 7 pi over 6 and 11 pi over 6. Notice I have an overlap, right? I've got 5 pi over 6 and 7 pi over 6, 7 pi over 6 and 11 pi over 6. So I just consolidate that into a solution set of 5 pi over 6, 7 pi over 6, and 11 pi over 6. Because the domain of the cosine function and the sine function is negative infinity to positive infinity, there's not going to be anything that's going to generate something that's undefined. And these are the two that you don't have to worry about. It's when you deal with any of the other four that you need to be cautious. So for this example, I have cotangent of x times tangent of x minus 1 is equal to 0. Okay, for this example, we're going to do exactly what we did before and take those two factors and set them each equal to 0. And then let's try to solve the resulting equations. So that means that the cotangent of x will equal 0 and the tangent of x will equal 1. Well, cotangent of x equaling 0, that's x over y equaling 0. So I'm really looking for where is the x coordinate equal to 0. All right, and so that's going to give me pi over 2 and 3 pi over 2 as outputs. And then where is tangent of x equal to 1? And that's going to give me, I'm looking on the unit circle for places where the x and the y coordinates are the same. And that's going to give me pi over 4 and 5 pi over 4. Okay, now notice that we have a tangent function and a cotangent function, and both of them have places where they're undefined. All right, and so let's think about this for a second. Let's consider the cotangent of pi over 4. The cotangent, that is just going to be the x over y instead of the y over x, and that's still going to give me a value of 1. Same with 5 pi over 4. So these values are good. All right. Now let's consider tangent of pi over 2. Now the pi at pi over 2, our coordinate is going to be 0, 1. And so if I'm looking at the tangent, I'm looking at y over x, so that's going to be 1 over 0, which is undefined. That's a problem. 3 pi over 2 is going to be the same situation, except it's going to be 0, negative 1. So I still have a 0 in the denominator. It would just be negative 1 over 0. That will be undefined. Okay, so if I look at my proposed solution set, I would have to eliminate pi over 2 and 3 pi over 2 because they will not actually work here. If it gets confusing, an alternate way to think about this is before you even begin, When you have functions in your equation that you know have restrictions on the domain where they would create something that's undefined, you can just identify those at the beginning, and if they show up in the solution set, eliminate them. So for example, I know that the cotangent of x is undefined where y is equal to 0, in other words, at 0 and pi. I know that the tangent of x is undefined where x equals 0, so that's going to be at pi over 2 and 3 pi over 2. If any of those values show up in my solution set, I can just eliminate them. And that may be an easier way to think about those restrictions. So for these next examples, we may or may not need to set the equation equal to 0 to start with, but we're going to need to factor. And we are going to look especially for a greatest common factor in these cases. So let's take a look. In this first example, I have sine of x plus 2 times the sine of x times cosine of x is equal to 0. So it's already set equal to 0. I don't need to worry about that part. So let's look at these two things. I've got two things added together, and you notice that there is a sine of x in both of them. That means I will treat it like a greatest common factor and factor it out. If I factor it out of this first part, I'll just end up with a 1 remaining. And if I factor it out of the second part, I'll have a 2 cosine x. So I'll end up with 1 plus 2 cosine of x as one of my factors and sine of x as my other. And now it's just like what we did prior. We will take each of those factors, set them equal to 0. We will isolate the trig function, okay? And so for this one, we'll need to move the 1 to the other side and divide by 2. And then we will think about which angles on the unit circle will satisfy these conditions. Which angles have a sine of x equal to 0? Well, that will be at 0 and pi. And which angles have a cosine of x equal to -1/2, an x value that's equal to -1/2? And that will be at 2 pi over 3 and 4 pi over 3. And so we can just express those as our solution set. Now this middle example, notice that I don't have my equation set equal to 0, so I need to do that first. So let's move this tangent squared of x to the left-hand side, which means I will end up with something that looks like this. Tangent squared of x times cosine of x minus tangent squared of x is equal to 0. And notice that in both of these pieces, separated by this minus sign, I have a tangent squared of x. So I will treat that as my greatest common factor and factor it out. If I factor it out of this first piece, I'll have a cosine of x left. And if I factor out of the second piece, I'll have just 1 left. So I'll end up with tangent squared of x times cosine of x minus 1. And if you're ever worried that maybe you didn't do this quite right, think about mentally just distributing it through. Tangent squared of x times cosine of x does get me this term, and then tangent squared of x times -1 gives me this term. Okay, perfect. So now let's set each of those factors equal to 0. Isolate the trig functions, and then find the angles that satisfy these conditions. Where is tangent of x equal to 0? Remember, tangent of x is equal to the y-coordinate divided by the x-coordinate, so where the y is equal to 0. And where is cosine of x equal to 1? Or which angles have an x-coordinate of 1? Okay, and so this will be at 0 and pi, and this one will be at just 0. And so we end up with a solution set of 0 and pi here. Since we're working with a function, tangent, that has restrictions on the domain, we definitely want to double check and make sure all is well. So what happens if I sub in this value that came from the cosine function into the tangent function? What is the tangent of 0? Well, tangent of 0 is 0, and that's okay. We just didn't want to get anything that's undefined out of there. And so we're all good. Now notice that in either of the other examples here, we're just working with sine and cosine. They're always going to be good because their domain is -infinity to infinity. And so those are going to require no further checking. All right, last example. What's our GCF? You should be kind of figuring this out by now. Our GCF here will be cosine of x. So we're going to factor that out, and then what will be our other factor. Divide that cosine of x out of both pieces, and you should get cosine of x times 1 minus 2 sine of x is equal to 0. Okay, set each of those factors equal to 0 and isolate our trig function in the right-hand equation. So sine of x is equal to positive 1/2 and cosine of x is equal to 0. Where is the cosine of x equal to 0? That will be where we have x coordinates of 0 on the unit circle, which will be at pi over 2 and 3 pi over 2. Which angles have a y coordinate of 1/2? And that should be pi over 6 and 5 pi over 6. And so that will take care of the solution set for this trig equation. That wraps up this strategy. In our next strategy, we will discuss how do we solve trig equations when there are more than one trig function in the equation, but it does not factor. So we'll do something a little bit different there, and I will see you then.